All right. Hello, everyone. Welcome. I want to start out and say that recently I started posting everything on social media. I have my Instagram, TikTok, and I'm also posting to YouTube Shorts. And it's been quite well, the reception. I'm really appreciating all of you liking and commenting. And let's keep this journey going. Keep going strong. It was a great start. Really appreciate it. Let's keep it up. Today, first thing, good. I got latest, merged everything. This is the state of the project, how it is today. We got some nice little spline. And our mission for today is I need to know more about the track contents in order to have better driving physics. One of the things that we're doing as a hover cart is we're hovering a certain distance along the track, but I have no concrete idea about what is forwards. The moment I get airborne, it's hard to determine what is the angle I should be facing. So I want to turn it into a lookup table. And one other limitation, and we'll probably have to look into this, what we did last time is we improved the accuracy of this spline. So we can now sample it and get accurate rotation and tangential information, and also the right vector and the up vector are all now correct. But since the spline is running here through the center of it all, what we don't want you to do is fly up here and then suddenly get recorded that you're over here. So yeah, we have to make sure we don't let that happen. But our goal for today is to take our current position, find out where we are on the spline, and then I'm going to convert that spline position into some sort of lookup that allows me to see what track am I driving on. And the reason we're doing this is that this track model, this is a complex model with lots of geometry. If we supply a simplified mesh, then we lose all kinds of material information from that mesh. And because of that reason, we're just going to do it differently. We have these spline definitions. Let's see if I can find one of them right there. So we have this spline definition. Oh, let me go and add some size to the mix. And this describes basic information about the track. And what it's also going to include in the future is an explanation of what the track is composed out of. These pads on the side, they're supposed to do damage. And you may have some kind of booster pad or a healing pad or a hot or cold pad on one of the sides. So you kind of feel preferential to one of the other sides. We're going to author that information into this asset here. And then during runtime, we figure out where on this huge spline are we? Where are we on the X and Y of this one on the spline? And this is agnostic of orientation. So over here, this diagonal would be X, and this diagonal would be Y. And that allows us to then figure out what's the forward vector, what's the up vector, without doing any queries to the collision system. So that's the plan for today. I had a different approach in mind. Luckily, we found out that all my conclusions were based on a bug. And now that the bug is fixed, we don't have to go that way anymore. So now that we have just some simple level with some clear changes in type, let's see what we're dealing with. So right here, we're reconstructing the spline smooth based on the output points and the output tangents. Okay, so this, because our input curve is not the same as our output curve, because we use our input curve to generate a bunch of spline meshes, we then use the spline meshes, the curve supplied for that, to reconstruct the track spline smooth. So that should be a very accurate representation of what we're dealing with. Okay, that's good. We do the start and the end, and then we draw a line in the color of emerald. So how many pieces do we have? 222. I'm expecting to see some sort of lines. Oh, is this a thing where we're evaluating? This is in centimeters and this is in number of points. Oh, we use the reparent table right there. Gotcha, gotcha. All right, so where are the splines? Now we are talking. So we can see for every segment, and I think a segment would be from here to here. We can see it draws a green line. It's hard to tell where it exactly bends. This looks right. Because of this density and the fact that the track is so insanely wide, we can't expect too much curvature on this track. Yeah, there's a significant lack of accuracy. So that may mean we are okay with just doing a lerp, where if we know that your distance is between this point and that point, now we just guess. This is the forward at that point, this is the forward at that point. Lerp it. Call it a day. Okay. So our input data looks good. Good spline. Good spline. Yeah, I'm gonna go for just a lerp, and we can always just subdivide the problematic ones. Although what I can just do is only have I'll only store the points, because right now, yeah, the end distance is the same as the next one's start distance. So what's our output struct? What we want to know is your up and your right and direction vectors. And these are, I'm going to call it your position. So we have our distance and position. So we want to find the track piece. I like to make the binary search exclusive. That's just who I am. I'm going to add an extra track piece in there. They're just there to support the overlapping area. Once we're done, what we're gonna do is do another track pieces. All right, so we got 2 extra wrapping segments, making sure that that during the runtime we don't have to do any wrapping here, and hopefully distance is reliable enough of a value to do the early wrapping for us. Now later, when the track has attributes, they're not going to be blended, they're going to be constant throughout the whole thing. What do you think about that, compiler? So we got the spatial track, it's private. Yoink. All right, hover cart, that hover cart state position. I need to supply the distance myself, get distance along spline. Got that. So we're on line 399. Here we have spatial track. Look at that. This is someone else's code, and you can just tell they're very diligent with their, if not shipping, then draw this thing. Some good habits. If I go from sample position, oh, I don't know the position. I want to know the origin of the track. No problem. So I go from track position to sample track position plus the sample direction vectors right times sample the position right. And this is a bit madness, but it's going somewhere. So that's the first one. The second one is to go from this right angle to one that is also including sample direction vectors up times sample position up. What is the normal color for X positive? X positive is red, so I'm gonna make it red because I consider right to be red. And I'm gonna call it green. I'm gonna call it green. Green for Y. Y is up in this case. Fine, Unity, you win. But only because we are in 2 dimensions. So if none of the math explodes, it's hard to tell. I'm gonna also draw a little debug sphere. And that's gonna be for the track position. So, origin of the track. It's faint to see, but there's a red line horizontally and then a green line attached to it. Some airborne? Yes, perfect. Oh, look at the old track. Yeah, that's bad. So I got detached from it. You shouldn't get detached. You should know you're forward at all times. Thank you very much. Got myself a coffee. Now, just for double checking, I'm gonna go just a little bit above the road surface. I'm gonna draw X, Y, and Z lines. So hopefully this normal is going to be a lot more reliable to use. So hopefully what I can avoid, now that I know the direction, what is your right, what is your up, what is your forward, I can avoid these cases where it's like, I have no idea, I'm just making measurements. Bad stuff happens. Cool. Let's pop that in the physics. Now that we know everything works correctly. So when we spawn contestants, guess who needs to know about this are the physics component and the camera. The camera may need special behavior, knowing what way is forward, especially at lower speeds. Right now it doesn't really know what to do. So at lower speeds it may opt into aligning itself with the track normal, track tangent. So the chance exists that different pieces of the track affect boost and heat in different ways. So that means, let's take the sample here. Now this probably means there's a lot of stuff we would be able to change. One thing at a time. Physics. Just takes a delta time. We're gonna get fancier and take a sample. And now what the compiler will tell us that we are missing something. Update movement's gonna get a sample. All right, then finally we have to include the thing. Oh yeah, this is the upright correction rate. When in doubt, this is the direction we want to face. This is one of the places. So instead of just taking Z up blindly, it's going to be a spatial sample. The up No. Direction vectors up. Cool. Physics relay. Physics relay. I don't think I'm gonna ever work with physics relay anymore. It was a good experiment, but it does have this virtual method. Boruki, initiate a respawn sequence. Okay, that's weird. That should have been going to the right direction. That didn't make any sense. This is weird. This angle shouldn't be this angle. Shouldn't be. I think it's going to be hard to test with multiple cards. You can see how the slope's going. So where is this extra angle coming from? Get more debugging. Get some better debug drawing. So we want the ground, direction, and vectors. Take a look at those. Just to verify the ground direction vectors, those are the ones we're going to be looking at. Go on here. That looks correct. As predicted, they're very erratic because they really just sample the ground. Let's see what they look like on a good slope. It's weird. It also, on these kind of curvatures, it bends me to the left. But this is weird. This is weird. This is saying something else. I remember we add a little thing to the mix. We add the current into the mix. And then we multiply it by 0. Okay, great. And what do we do then? Is there something wrong with this normalize orthogonalize function? Right, I can just see what it looks like. They'll probably be of arbitrary magnitudes. All right, for starters, Z is missing. And that's fine because we're reconstructing forward and right, and then we'll figure out what Z is. So Z, so forwards, that looks like the correct slope. That looks like a correct angle too. But then you can see after we apply the normalize and orthogonalize, the right vector just jumps up. The Z vector gets created, and the forward, I mean, it also gets normalized, so it just, the length gets fixed. So that is quite problematic. That's quite the weird correction that only happens to the right vector. I think this is the wrong approach because we're putting so much effort in computing forward and right, and then we're putting 0 effort in actually just doing a cross product and getting the last value. I think that's basically it. And I'm sure the normalize and orthogonalize function normally works, but not where we're doing it. Now, I never remember the order. Copilot says it's forward and right. I'll take it. Hang on, I think this will really improve the quality of it. That looks a lot better. Yes. I think that was what was missing. Some boost. 500 kilometers an hour. No, didn't make it. This is still a weird corner, and I don't know why. Do I have an air upright correction? So it's 0. It's hard to read because there's yellow text behind it. It's 0.08. If I fly up, oh, it turns into 1 right away. All right, so that in combination with a rate should align me with the track pretty fast. I'm going to cheat. Upright correction rate. Hard-coded to 1. Hard-coded to 1,000. The debug value is 0.1 right now. Well, I'm uprighting to something. I have no idea what it is, but it doesn't look like it's that upright. Let's do another drawing of this one. Draw get world. We're just gonna differentiate it by drawing it above us. Oh, that doesn't look good. So what is this? Oh, we checked these. These look awful. Getting the sample here feels like we're sampling the wrong position along the track. We can verify, hopefully. What is going on? All right, let's look at if everything makes sense. So we have a distance. It is 444,000. And if we look at the segments that we have, near the end, okay, 44,524. So we should find 221 and 222. We got 221, 222. The segment length is 1,523. If we subtract the position from that, what do we have? 336, 366. Yeah, that is all correct. So the blend is somewhere in the nicely in the middle. The actual position, that is off by a lot, and a lot. That's the weird part. This thing over here should look like that thing over there. So the distance along track is 73,800, and in the game race mode, 8,600. That's a different value. That's not even close. Okay, so get distance along spline at location is what we do in one example. And in the hover cart, get distance along track, distance along spline. This is from spline track. Oh, okay. So there's an offset. That explains. Yeah, that's just confusing. Yeah, feels like it's lagging behind, but I think that's just visual. I feel like that's trying to upright me towards a better direction. Yeah. This all looks solid. And I'm just looking at the debug data. I'm not even driving the car. So what about this bend here? This bend's always... What's that? Why is that? Oh. Oh, this is rare. Haven't gotten stuck in geometry in a very long time. Cool beans, as we say. All right. Happy, happy, happy. If I don't look happy, it's because there's still a lot of work to do. Motivation is everything. I'm gonna get rid of this thing. Look at the beauty. Look at the beauty. Bam. Deleting didn't actually update it. And bam. That part I'll forever have to investigate, see what's happening there. I am happy with this. So what is my current goal? My current goal is that white theme. Let's be a little bit more subtle. Current goal is we're driving along the track. This is the track. At any point, the cart wants to hold a certain distance above the track. And there's this imaginary thruster that may or may not visually exist on the cart. We don't really care. But that is saying, if I'm over here, I should add some force upwards. And not just that, if it has a desired place and also a desired velocity. So at this point, the desired velocity will bring the cart upwards. And that is designed in such a way that it will work at any orientation and any velocity. And that also means that it gets dampened. So if you land straight down, at one point, like let's say it's over here, it will start to say, okay, I need to start following through towards this target velocity. And the lower you are, the more oomph you have to reach your target velocity. And your target velocity here is positive. Your target velocity here is negative. Your target velocity here is a little bit negative. And just by doing that, that's how the cart keeps upright. What is completely missing from this equation is that if I'm over here, my target velocity is negative. If I'm facing this way, I don't need to do anything because I'm accelerating towards the ground. So maybe what I should do is have this height balance be determined by my rotation, and I should affect the rotation based on the track normal. And I think changing my orientation that way will make it nice and dynamic, hopefully. So let's continue with that. We got our thruster trace. Well, it records the distance based on the body of the carts. We have our compression, and the higher we compress, the more surface we have to press off against, so the more control we have. And lastly, we have our upwards thrust, and our upwards thrust is a little bit cheaty. And this lerping here is because it's not going to affect you immediately. It's going to be smoothed out. So that just introduces a little wiggle. And I like having a little bit of a wiggle. And here we're doing it with the impact normal. That's a weird one. Not even the trace normal. So just to be sure we're working on the right thing, we should just fall to the ground. Block. Now we're just gliding. Which is also a game, which is also a vibe. We're just one term removed from making it a kart racer. Game feels surprisingly well for something where the kart doesn't hover. So this is great. What I want to try is orient the vessel in the proper direction. What that would mean, if I have no velocity, I wouldn't be flying. And if I have any velocity, it should keep it upright. And I think once I have it upright, at that point, I can do the blending of the two solutions. One where it fixes the orientation, the other one where it has this imaginary force. Because what we want you to have is when you're standing still, we still want you to be off the road surface. But I don't like how fakey that force is, if that makes sense. If the road goes like that, then over here, I want to be a certain distance away from the track, but this was my direction normal there. So here, this is my current direction. And the direction I need to be at is probably that, but that's some predictive stuff, and we're not going to do predictive stuff. But the least I want to do is be online with the surface normal. If I can be online with this is where I'm gonna be, so I think the easiest thing to do, my pitch should be of a specific value so that I'm always going in the right direction. Let's cheat it. So I have a double target pitch, and this is, if it's positive, I should aim upwards, and if it's negative, I should aim downwards. So I don't know what this number is yet, but it's magically just gonna be scaled by this constant. And I don't even know if 0.5 is of the right magnitude, but one thing at a time. So we have our desired pitch. Now we need to know what our pitch is. How do we know that? How do we know that? We have our spatial sample. If I dot this with the state forward, probably. So if this is positive, then we're aimed up somewhere. Yeah, this is not something I usually write, so I'm just going to do the first thing, and that's just to log it all. I'm going to re-enable this because I need it now for testing. So when the track curves up, I expect pitch to be a negative value. It's a positive value. When it tracks down, I expect the opposite. So I shall just negate the thing. Yeah, that makes sense. That makes sense. All right. So I got a good pitch. Now, my target pitch. This number is probably going to be whack. Especially since I expect it to be mostly 0. Oh, but I guess what it also does is it is offsetting gravity. So this one's saying I should still point up. And now that it's getting compressed, it's more up. And now that I'm curving down, it says less up. I'm also expecting that I'm not at the perfect height. Oh, getting close to the ground, it really says pitch up, pitch up, pitch up. Can I get a negative value out of it? Yeah, there's also some ground gluing, so it also does negative. However, what was the value I saw at the peak? 490. Let's do that. So it says go slightly up. Go a lot more up. Go a lot more down. Go a lot more up. Yeah, I'm still going to multiply the final value. So good stuff, good stuff. Oh, the lamest solution would be to say current direction vectors forwards. Very, very cheeky. Oh, the real test would be if I get rid of the upright thing. So now it should be pure card velocity pressing me up. That's very up. That's sort of like it. Math is clearly broken. It is surprising how it doesn't have liftoff. Expected the acceleration at this angle that it would do a lot more. That's weird. It's that one corner. So bad. I'm gonna do a draw debug line from... I want to visualize where this change in direction goes from. And it feels like that's the correct direction. All right, re-enable this. Let's re-enable that. It looks weird when it happens. Another reason it looks weird is because it happens after we do the collision resolve. So you should be flat on the ground. But we can make it a little bit more subtle. And one thing it should help with is before you land, it will get the right orientation. That weird corner, man. Just make it more subtle. Because it doesn't look so great. And I want it to be dependent. Instead of having the magical division by 450, I want to do the lookup based on a different way. You can have a different curve that's tweakable. And when the way it applies, it's not a rate, it's not a force, it's just, let me yank this one pivot. Nice. It feels a lot better to drive. I'm gonna disable all the debugs because I want to see what the game feels like without looking at the debugs. And having debugs on screen, very, very distracting. There we go. There we go. Cart angling depending on the surface. There we go. It's like panicking. Tries to stay correct with the surface. It needs some love, but here you can see, oh, trying to avoid the road. Nice, nice, nice. Panicking a little bit. I wanted to have the impact on landing where if that happens, it kind of punishes you because you have the impact, it changes your orientation, kind of screws with you a little bit. So you should have picked a better race line, probably, if you want to go for the optimal times. Let's go a little bit faster. Oh, you're still invulnerable. All right. Yeah, no, I'm happy with this motion. It feels a lot better to control. Let's see what the most problematic corner of the game does. How does our cart react? Poorly, but that was because of my driving. Eventually, the collisions on the road mesh are going to be replaced with simplified collisions, not ones that are so complex with gaps in it that allow you to drive through it. So, not worried about that. What I am worried about is randomly flying up in the air. Can we reproduce that? I feel like the speed has diminished. I'll have to investigate that. Here we go. Good behavior up until the point that I drove off the track. But normally at that point, I just fly in the air. So that's a big win. I love it. I love it. It's the driver frantically trying to pull up to avoid a collision. There's this physicality to it all, and it still has to be improved. I really want you to go up and down, bounce a little bit here, but you know, you get a feel for the cart and you know what kind of turns, what kind of bends, what kind of twists it can deal with. And if you are messing that up, that's on you. And it also means you can choose your path. You can choose to take a ramp, you know the repercussions. Nice. 3 minutes, 1 second. Terrible time. I could do a lot better. I think I have someone who wants to say hi. Hi. Come eens hier. Go, go, go. He's tall enough to open the door. Beautiful. Go wave goodbye to the people. Hey, Zaya. Zaya. You enjoying a little biscuit? Dusha. All right. Thanks for tuning in. Yes, Jam Socks. He's getting so big. Nothing's safe anymore. Anyway, much appreciated. Take care, everyone.